Good morning, everyone. Thank you for being here on this very early morning session. I've never done a session at 8 a.m., so it's going to be a first. In fact, my alarm just kicked in. Interesting. So hello. In this session, where we're going to talk a little bit about continuous profiling and how it can fit into your existing observability stack, and what is actually what we mean by continuous profiling. Before that, the boring part, I'm Mohammed. I work in an audio streaming company called Spotify. You know it. As a backend engineer, so I do a lot of Java monitoring as well of the applications that I contribute to. And I'm also a Google developer expert for Google Cloud. And spoiler alert, this presentation contains a lot of images, and those images are mostly generated by DALL-E and ChatGPT because it's convenient. It also offers super realistic kind of images. And this one I just asked for an on-call person waking up in the middle of the night, struggling to fix an alarm or an error that is happening. And it's, oh my word, it's super realistic. Who has been on-call or is on-call? Yeah. You know how it feels waking up at 3 a.m., making that first cup of coffee and trying to figure out what's wrong and bringing the application healthy. In fact, I'm going in on call in a few hours, so wish me luck. Before diving into the actual subject of this presentation, let's go back and analyze the journey of how we architect our applications. So this is how the majority of the application in the 90s looked like. It was simple flow of communication between the client of the server. All the components of your applications were tightly packaged into one single executable. We used mainly one language to run the whole application. The issue is, this is probably going to hit you hard when you want to scale. So in order to scale, we started to look to implement new ways of architecting our application. And we started to split the monolith into smaller services. And those services collaborated together either by passing simple data or achieving some functionality, achieving some means for the user. And for that, we used smart pipes. And those smart pipes, there were basically two main categories, either enterprise service buses or MQs. But it was both, from an organizational point of view, hard to implement, and also from technical perspective, it was kind of challenging. And to scale even more, in 2010, we started to make our service even more smaller. And we moved it toward dump pipes, decentralized communication. We used different language as to run our applications, whatever language fitted our needs. We went to that. And yeah, this, however, introduced a lot of complexity. We moved it from simple diagram of tracking our application into a complex architecture. And this is ChatGPT imagination or interpretation of cloud-native complex architecture. Interesting. But the thing is, distributed systems at scale follows what we call Murphy's Law. And it says that anything that can anything that can go wrong will eventually go wrong. When we added more instances, means that more instances of anything that we have can actually fail, probably even at the same time. Distributed systems or components and services in distributed systems no longer start and stop in a predictable manner. Gone are the days where you stop your server or you start it and the issue is fixed. Services can change their state, their behavior, their version, and that cause a lot of issues. One of those issues that when we move it to those loosely coupled distributed systems is observability. And observing the interactions between those services become more challenging. Instead of focusing on one service, having everything in there, logs and stuff. Now we have to trace back all different components and follow the request journey in different components, which introduces a lot of points of failures and also a lot of challenges, both from observability and other things, traffic, security, and so on and so forth. And when we talk about risk management, there is kind of a known framework that we use. It's used from defense folks and stuff. It's called the Johari window framework. How many of you are familiar with this framework? Okay, so it has 4 basic components. So it categorizes any risks at 4 major components: known nodes, unknown unknowns, known unknowns, and unknown unknowns. So I dropped the unknown knowns part because, like mostly in software engineering, we can categorize the risk into 3 major categories. The first one is known knowns, which are basically the standard fact that we are known within your team, within your organization, and industry-wide facts. Things like having an infinite loop will break your application, because like you will run off out of CPU. Using more resources than declared in your container, the container runtime will basically halt your application because it's past the amount of resources it allows to have. Things that are facts and that we are aware of, kind of in the software engineering. Known unknowns are the things that slip through, but the moment you see it, kind of a bug, you know that, oh, if I just knew it, I had this in the bucket, it just like slipped through. Things like a bug that's kind of a bug that the moment you see it in your observability stack, you understood, oh, this is a quick fix. But then it passed your checks, it passed the peer review, it passed everything, and then went to production and slowly started to cause production. And it's kind of quickly catched by some of the observability tools that we have. And then we have unknown unknowns. And that's where all the incidents come from. The things that we struggle with, we don't know about the system, or fail to understand from both a business point of view, architectural point of view, and they slowly start causing problem. Like a small memory leak that is hard to catch in your production environment, but it's slowly causing issue to your users and causing slowness of your whole system. And for years, we relied on what we call the pillars of observability. By the way, this is also generated by DALI, and there is typo in traces. So it generates very good images, but it doesn't know how to spell things. And I was saying we relied on what we call the 3 pillars of observability: logs, metrics, and traces. Very briefly, logs are more textual information, very easy to get, very easy to set up. They can be overwhelmed sometimes because depending on the amount of the logs that we generate. They are contextual, as I mentioned, and they are textual and contextual. So they are mainly texts, but they introduce context. We can add more context to them, which request ID, from which user, from which context, from which thread, and so on and forth, so forth. So they provide more context about what's happening. They are easy to set up, and we can tweak them depending on our needs. If there is a bug, one of the first reflexes we have nowadays is just like add a log and try to check the path of the request. And they help to understand and establish the why this is happening, why this function is not returning what it's supposed to do, why this code path is actually getting invoked while it shouldn't. So it helps to understand the why and provide us with more context, with more information about the execution path of our code. The second technique or tool is metrics. And they are more statistical, more numerical, and they provide a high-level overview of the system. They generate throughout the lifetime of your application, your system. We get them, we ingest them, we analyze them, we gather them, and then we have kind of some sort of visualization where we get the bigger view of the system. They help to spot mainly the resources and how the system is behaving from a resource point of view. The KPIs include CPU consumption, memory consumption, request time, aka latency, and they basically give the health check or the system health information, and they help to spot bottlenecks and hotspots. And the last one is traces. And traces was introduced when we moved to more distributed systems. And they basically help to trace the journey of the user request from all the systems and all the services that it went through until the final application. And it helps, again, to detect where the bottleneck is in your application. And it helps to detect causality, like cause to effect, and what causing this slowness in my server or in my service, and why it's actually slow. So it helps to detect bottlenecks and react over it. And while I was happy about the images I generated by DALI and I was impressed, I shared one on X, previously known as Twitter. And I shared the 3 pillars of observability and said, like, DALI can understand what I'm saying and generate nice diagrams without worrying about the copyright and the resources. That's someone else's problem now. And then my dear friend Jonathan, who is part of the pivotal Spring team, who works mainly on Micrometer, it's basically a monitoring tool. And he worked on the Spring observability team as well, I believe. And he was kind enough to trigger this. Like, he said that observability should not be defined with pillars, which is completely true. In fact, the amount of pillar doesn't matter. They can't show the whole picture. And what he's trying to say is basically we need, no matter the amount of pillars, no matter amount the tools that we have, if they don't coordinate together to get the bigger picture from the different components, they can never give you the whole understanding about how your system is actually reacting. And back to Johari framework, the 3 pillars of observability, or at least metrics, logs, and traces, excel in giving you macro-level understanding or macro-level indicators of how your system is actually behaving. Logs, in fact, excels in giving us or helping us to understand the known knowns. Like, if there is a small issue, it helps you to detect that issue, why this request is, or why this method is not returning the result it should, right? The combination of 3 metrics, logs, and traces helps you understand the known unknowns. It helps to gain confidence about the things that we don't know about our application, gain an understanding about a bug that has been hunting us, the system is running out of resources, the things that we usually miss, but combining the 3 of them help us understand the overall performance of your system. And then there was something missing, which is in the unknown unknowns. And that's what profiling gained momentum in the last years and trying to fit in and complete the picture on the observability stack that we have. And you can think actually of profiling. The analogy that I like to give is you can think of traces, logs, and metrics as the metrics that help us understand the human body, like blood pressure, heart rate. Those can give you basically the symptom, temperature of your body. Those can basically give you the macro understanding of how your body is reacting, if you're sick or not. Profiling, on the other hand, is similar to the X-ray. It helps you to understand how your body is actually reacting and goes beyond what is actually appearing. So what actually we can get from, what information can we get from profiling? The well-known one is CPU profiling. And CPU, basically, it helps us to understand what function, method, code block is actually consuming the most amount of CPU. It helps you basically get a lot of sampling and gets you the most executed code on your application and help you to answer the question, what is consuming the most of my CPU? Workload profiling tries to answer the same question, which is what is consuming the most, but not only focusing on the CPU. It could be memory, could be I/O, could be network, could be a lot of things. But it's more general than only CPU. A subcategory of workload profiling is more specialized on lock, thread, and stop-the-word profiling. They are kind of a subcategory of workload profiling, but they are more focused, more contextual around one thing, like threads. Why my thread is running slow, both, or why I'm running out of memory for that thread. Why there's lock happening. Why there is a stop the word in terms of garbage collection and stuff. So they are more contextual, more focused into some scenarios that happen into your system and can affect the performance of your application. Allocation profiling mainly answer what is allocating the most resources in my application, and that's from a memory point of view. Why my application is taking that much memory, and why we should be worried about memory, especially in a Java context. The more memory they consume, the more later the garbage collection needs to do more work, either to organize that memory or to clean it up. This is becoming less and less issue with the new garbage collectors, such as ZGC and stuff. But still, if you're using old generation, stop the word kind of garbage collection, will introduce a lot of stop the word garbage collection operations and might affect the performance of your application. And the final one is heap profiling. And heap is, as the name suggests, focused on what's on my heap. And that understanding what's in your heap help you to optimize what's in your heap, basically, and fix or understand the issues such as memory leak or optimize the whole amount of memory needed to run your application. For profiling, up until recently, we were stuck with what we call traditional profiling, or just profiling as is. And those were pre-production kind of tools. There were two main categories. There were either desktop-based, meaning that we need installed in a developer machine on a rich client environment or rich client thingy that's run on the developer machine, where the developer try to profile the application and do his best in order to understand what's happening, get information about the health of the application, and try to reproduce the errors that is happening actually in production. The second category is APMs, like agents. And those were also pre-production environments because of mainly the overhead that they were introducing was not bearable to run in production. They introduced a lot of overhead, and that's why when we have them in QA, development, testing, you name it, but they were only pre-production environment. Both of categories in profiling or traditional profiling fails to give the big picture because like they are not run on production, and we were hopelessly trying to reproduce the same issues, the same patterns that were happening in production, and sometimes we succeed, sometimes not. So that's why they have limited visibility, and the symbols were also missing from a production point of view. Symbols are basically mapping between machine addresses and your code. The machine doesn't need human readable format, right? But we does, like which functionality is eating much of my CPU. Think of it as your contact list in your phone. If you're having a messaging app, basically, it would be hard to map which chat is to which of your friend, relying only on phone numbers. That's why we use nicknames and usernames or names to map which person is which. So symbols is exactly that, but from a CPU level, understanding what your application or what is running in my CPU, in my memory, in my resources, and attaching that to a human readable format. So when we profile it, we get the profiling results back, we understand what's happening. So traditional profiling, what you need to understand, they introduced a lot of overhead. We couldn't run them into production. They offered limited visibility because we can't run them into production, and they were missing symbols. And Josh Long, you probably know it, the Spring developer advocate, as he likes to introduce himself, says that production is the happiest place on earth. And that is true, because like your code actually lives in production most of its lifetime. That's where you are aiming to push your code to. That's where code live. That's where the user came in to get value out of the code, run your code, meet bugs. And that's where the business gain money from, and that's where the business as a whole introduce value, right? And running profiling information in pre-production environments, we're missing the fun, right? We're missing where the actual action is happening, where the actual fun is actually happening. So continuous profiling tool try to exactly fix that. And if there is one thing you need to get out from this presentation is that profiling was introduced a lot of overhead. We can't run them in production. Continuous profiling tools, the new generation of profiling tools, have a low overhead, between 2 to maximum 5%. If there's a profiling tool that is consuming more than 3 to 5%, it's not a continuous profiling tool. So the overhead is very minimal from a production point of view. So they are kind of, they have low overhead, and they added this time-oriented dynamic view of how your profiling is. They provide your application 24/7 rather than ad hoc. They continuously profile your application. That's why the dynamic and time-oriented part came from. They have low overhead, and they are well placed for the complex cloud-native architecture that we are running nowadays. And yeah, sorry. 8 a.m. morning. Okay, thank you. Can I back? Yes, thank you. And they have low overhead and production friendly. And continuous profiling is not actually new. So it's gained momentum a lot lately, but Google had a paper, and that's, by the way, a QR code. It's crazy what we can do with Gen AI nowadays. So the QR code will basically take you to the paper. But the paper was published in 2010, and you can assume that Google were running it years before it was actually published. And basically, it set the base of how actual continuous profiling tool are looking like. And this architecture will basically be replicated in all the new continuous profiling tools that we're going to see in a minute. But yeah, that's to say that continuous profiling is not new. Google launched the paper in 2010, and then a lot of companies followed, but they didn't publish it, such as Facebook, Netflix, and such. They have their in-house tools for continuous profiling based on Google paper. And with the paper, Google also introduced a new format to ship profiling information. It's called pprof, I believe, and open source tool that does the same in Go. So from 2010, there was mainly in-house things, and then in 2019, Google introduced profiling as part of the GCP suite offering. Amazon offered the same thing as well. And then 2020, 2021, we started to see a lot of new generation open source profiling tools. And a lot of startups such as Periscope from Grafana, Pixie, and those folks. We'll dive into it in a minute. From an architecture point of view, they more or less all follow the same architecture that Google introduced. In order to get information, you can either instrument your application, add in some data, add in some sampling information in order to extract the data the profiling information that you are interested in. Sorry. To get profiling information, the second thing you can do is rely on agents. And basically, they collect information on your behalf, but they are more general. They are not specialized to your business. Once you get those profiling information, you ingest them. You clean those information up, you categorize them, and then you send them to the profiling. And profiles are basically the core of the continuous profiling system, right? And profiling is always missing without symbols. And that's, again, what you do the mapping between machine address and into a human readable format. When we collect those data, we need to store it somewhere. And depending on the tools, there are different storage strategies. Could be long-term, could be short-term, depending on your need. Some things like Pixie, we're going to see in a minute, store it for a short period of time in cluster. Some others like Periscope do the analysis and storage outside your cluster, and they can store it for a longer period of time. In continuous profiling, you won't basically face an issue with this whole part up until storage. Storage is the tricky part that you would need to figure out, because especially on relying on agents, they continuously get information 24/7, and the amount of storage you will end up with is gigantic. Facebook launched a paper had a paper a couple of years back on how to basically compress this data without losing the big picture, but still. It's one of the biggest concerns and biggest challenges that you will face moving to continuous profiling. And then the final step is we need to get this data back in a nice diagram, in a nice visualization. And for that, you would need some front end. And again, the flow, pretty simple, pretty straightforward. You need to get some data from your profiling tool. We get the data, we ingest it, we clean it up, we analyze it, either long-term, and then from following the analysis, we generate some visualization to enable us to spot bottleneck, to spot issues, and to optimize the code of our application. Techniques. There are different things or different kind of techniques of types of profilers. Event-based. You are mainly interested in some events. Could be some block IO events, particularly interested in, let's say, a request that goes to the database, whatever. They're event-based. You are really interested in some events, and you're profiling those events whenever they happen. So once they get triggered, you basically give the information and profiling information for that specific event. Instrumentation profilers requires instrumentation, and by instrumentation, as I mentioned earlier, is basically you going into the code and adding checkpoints. When your application is running, you have checkpoints, and whenever that checkpoint is hit, it gets profiling information, but it requires manual setup. Sampling information, the most straightforward, most easier one, is basically getting sampling of the execution of your application. Whenever we get sampling, the collection of them will give you an overview of the most executed function / method / code block in your application, and will give you a nice overview of in a flame chart format. We'll see that in a minute, but it basically give you what is running the most or frequently in my application. And that will help you to get understanding of what the hotspot is, and if it does make sense. Thresholding profilers, it's a kind of subcategory of sampling profilers. But you want simple until some threshold is triggered. Mainly if there is a write into the disk that is taking more than 10 milliseconds. You want to understand why this is happening. What type of operation, what address is coming from, what request ID. So it's a subcategory of sampling profiling, but when a threshold is reached. Basically to lower the amount of data and lower the amount of the things that you need to worry about. Continuous profiling is not all happy and good and panacea, right? We still face some challenges moving to continuous profiling, such as symbolization, especially when you are dealing with instrumentation profiling. Getting those data, putting the metadata in order to make it human readable format is still challenging. Less compared to previous, but still, it's one of the challenges that we have currently in continuous profiling. Data collection, I mentioned that before. It's again one of the challenges of continuous profiling. We are getting the data 24/7. The amount of data we get is gigantic. So how we deal with the data, how we effectively store it, how we can effectively analyze it is one of the questions that we would need to figure out. Correlation with other signals, again, back to no matter the amount of pillars you have, we won't have the bigger picture or the whole picture. We'd need to correlate with other events. Correlation with metrics, logs, and traces to have this whole picture. And Periscope excels on that in a way that, Periscope and Pixie, I will get into that in a minute, so keep focused here. Widespread adoption. Continuous profiling started to get momentum lately in 2020-ish, as I mentioned. Some of the tools are not widely adopted. So we would expect that some of the features that you probably want for your specific use case is not yet there, but still, it's reached a huge state of development and advancement compared to the past years. Representative sampling, what information you are speak more sense to you. You're getting a lot of information, tailor it down and tweak it down into what exactly speaks to you. Doing some tweaking would be needed in order to know what you're focusing about, rather than just generic information that it would be a noise more than helpful. So why we would be interested about continuous profiling? The first one, and the obvious one, the promise that everyone's trying to say whenever it comes to selling tools to others, is cost saving, or that's the promise. And why it's cost saving? Because when you introduce continuous profiling today, it will add an overhead, 2 to 5%, right? But in the long run, as the continuous profile tool is running, hopefully you would detect hotspots, the things that are consuming the most resources in your application, be it memory, be it CPU, be it other things. And while you're getting those information back, you're optimizing your code, either to use less CPU or use less memory. So you are either lowering your cost bill, right, by optimizing the resource consumption of your application, or if you are not on the cloud and having your own cluster, you are condensing what you can run in a single server. The application will use less resources, and then the amount of applications that you can condense in one server will increase, and that you basically will have reduced costs. And that's the promise. It's not always true, but yeah, it's a thing. From a developer experience point of view, we got a better feedback loop, in a sense that you deploy your application, it's go through the CI/CD and all the usual check, and then once in production, we will basically get information about how our application is performing from a resource consumption point of view. Did we introduce a code that is using much memory than it used to be? Did you introduce a bottleneck from a CPU point of view? So continuous profiling can help us improve our code and understand the bottlenecks or the hotspots in our code, basically. And other things, proactive troubleshooting. while using profiling tools and continuous profiling tools, it will be a habit because like the data is there. In your morning, while you're having your coffee, check in what happened the day before, check in the trend from a CPU point of view and the resources point of view, and check if there is anything wrong with your application, or there is a function or a method consuming more CPU time than it should. Reduce downtime, hopefully, and that's by mean on the proactive side of things, fixing issues before they happen, or even if they happen, you will have from a code level point of view, because continuous profiling, I forgot to mention, that gives you an overview on the code that is running, both from the user space and also from the kernel space. Meaning that you will get an overview not only from the code that you write, but also from third-party libraries and code running on your machine. Business resource utilization, mentioning that a lot, not gonna bother with that, or again, improved application performance, especially latency, CPU utilization and memory utilization, the hotspots, fixing them would speed up, hopefully, your application, and that will cascade as a better run for your application and hopefully reduce the latency time. Holistic view across the whole stack, again, because you are getting a view over the performance of your code, not only the code that you write, because that's generally 10 to 30% by max, but from third-party libraries and also the infrastructure code. Performance regression. Some tools offer difference view between the code that you write or the code that is actually in production and the new code. You can have like canary deployment or blue-green, or comparing to previous versions of your code. So having those side by side, you can detect if you're introducing regression in the code and the code become more slow or using more resources than it used to have. I asked it for Dali for another image of those things, and he ended up with pillars. So that goes in contrary to what I mentioned before, but yeah, Dali it is what it is. It's kind of a standard within our industry to mention logs, metrics, and pillars and represent them, and the traces and represent them with pillars. But yeah, that's basically to say that no observability tool is complete without the coordination of other tools. How we can acquire profiles? Two things. They can be either language specific. Things for Java application, JDK flight recorder, or async profiler. I will go back in a minute why these two and not others. And that's basically because they don't suffer from the safe point bias. In Go application, you can use pproof, Rust. There is other application, Python. So there are language specific profile that will help you to get the data and basically share it for analysis and ingestion and so on. How many of you are familiar with or aware of safe points? Okay. So safe points are basically a mechanism in the JVM that enables it to halt the threats. What happens is it adds checkpoints or marks in your either before and after the execution of a method or an execution. And it won't perform some operations until it reaches that safe point. Be it like GC collection, get all stack traces where all the profiling rely on the information that's what's running on your application. So it won't actually do or perform some application until it reaches a safe point. And that's for to make sure that you are not blocking anything or doing anything that shouldn't be done from a JVM point of view. So once it's reached that safe point, it performs some operations, such as GC, for example. Profiling tools relies on get all stack traces, basically to get what's running in my threads, what's my application, what my threads are doing. So when you send a sampling information request, like I want to get what's my application is doing in instance T, right? Which is the green arrows. The JVM will say, no, I can't do that now. Let's wait until we reach a save point, and then it will delay the operation until it's to the red arrow. So we are not getting the exact information when you ask it for, but getting the information when we reach the save point operation. That's what we call the save point bias, and that's a lot of traditional profiles suffered from. There is a good blog post back in 2016 that goes into the details into why most profiling in Java sucks, and what goes into explaining what the save point bias basically is. A good one. So that's basically the save point bias. It's a little bit more complicated than what I mentioned, but you got basically the idea. The JVM will basically delay some information until we reach a save point. It gets even worse with the sum optimization that the compiler does. So the save points are introduced by the compiler, and the compiler does a lot of optimizations in order to speed up the execution of the code. For example, inlining. If you have a simple method, instead of having a reference to that method and sending the CPU to execute the instruction of that method, we basically align it and make it in the body of the parent method. That is good from a performance point of view, but if you are relying on profiling information, it introduces the bias as well. So you won't get what's actually running on your application, but a biased view of it, which basically in this scenario will get all the service do something method rather than what was running before that. GDK flat recorder async profiler doesn't suffer from save point bias, or at least that's what they said. Another type of acquiring profile is eBPF. eBPF is a new functionality within the kernel that enable us to make the kernel programmable. It's kind of a framework interface that we can execute code in the kernel. I made this joke at Devox because I had a full session around eBPF, but the eBPF community says that eBPF to the kernel is what JavaScript is to the browser or to the web. I remember the days when we had those static applications, boring, with HTML only. When we added JavaScript, we added this dynamic version of it. eBPF is trying to achieve the same thing, but from a Linux kernel perspective. How it works, very briefly, we write an eBPF program, we compile it, code generation to the bytecode, and then we want to load that bytecode into the kernel. Before it gets loaded, there is a verifier that makes sure that the code is correct, both from a security point of view and also from a programmability point of view. There are some restrictions within the kernel. If you ever work with eBPF, the verifier is going to be a nightmare, because it tries to make sure that the code that you're running is safe, but it's tough to work with. But once you pass the verifier, then a JIT compilation run, which take the bytecode and run it or compile it into native code, and that's when it gets loaded into the kernel. So it's fast. So it's fast because it gets compiled into native code into the kernel. It is sandboxed because of the compiler. Make sure that it's secure, and you can basically have an overview or understanding of anything that is running on your machine. Since it's running within the kernel, and everything, if you're running on Linux, it's running, goes through the kernel, be it process call, disk call, network call, you name it. So you get an understanding over all what's happening. eBPF is event-based, so whatever happening, it will basically trigger an event, and you can hook your program to listen to some events and gather profiling information. And a lot of profiling tools are basically relying on eBPF, or at least support it in some way. We're getting close to the end. Oh, I still have 6 minutes. I need to speed it up a bit. Open source tools. We're focused on 3, and that's because they're more and more gaining momentum within at least the open source community and the cloud native world. The first one is Parka. So Parka is an open source profiling tool that is built with eBPF. It supports both being installed in a single node Linux machine or within Kubernetes, KWS, K8S, oh my word. It has a REST endpoint that enable it to either be integrated with your application to send profiling information, integrated with your CI/CD tools, and yeah, you can rely on it if you want. It had a good security level of detail of the architect decision that they took in their website, which is I find really cool, especially when you are talking about profiling and things that you put into your production server. Again, the architecture is pretty similar in all of them. We have an agent, or you can have instrumentation in your application sending data. They rely on the preprof, so they are using Go, preprof format to send data. It's heavily inspired from Prometheus. That's why you see some components that have the same name, such as the service discovery and stuff. And they have a web UI that you can visualize the profile information. Second one is Periscope, and it follows the hybrid approach, meaning that they have specific agents that they run in their in the server, or you can use eBPF as well if you want. They excels, or they claim that they excels in the storage part. They are more efficient, and they support different object store, S3, Google, cloud storage, and they claim that they are multi-tenant. So as I mentioned, they can use agent, and for the Java application, they rely on the JDK flight recorder, send that information to their servers, and then they will do the analysis and show you data. They rely on Grafana for sure, of course, because like it's a Grafana project. Pixie, my favorite one. It's a CNCF project, sandbox for now, using eBPF. It does continuous profiling, but it does more than that. It's more of a monitoring tool. So it collects some logs, it gets information, some traces. So it's kind of a little bit from everything. It's kind of a one-stop shop, they aim to be. They are part of the New Relic. So they first were developed in New Relic and donated to CNCF, and New Relic are still the main contributors in there. Hello? Okay. Wow. It looks, I need to change the colors. But yeah, similar architecture, agents sending information that is analyzed and shown back in a visualization diagram. Very briefly, what's next? eBPF is getting more and more momentum within the CNCF and cloud native community, and probably it's going to be the unified way of collecting the information. It's getting more capabilities within the kernel, and the more features it have, the more capabilities it have, the more we can expect that this new technology will gain more and more momentum, and probably it's going to be like the standard way of doing continuous profiling, especially that it has low overhead and almost native execution within the kernel. OpenTelemetry are working on standardizing also the continuous profiling format. There is a effort ongoing since 2020, but still they have a monthly discussion that we can join, and everything is open in an open source way. Okay, I wanted to show a quick demo if I can. I still have 2 minutes. But this is Periscope, and they have an application that is running here. It's basically a Docker application, Java application, Docker application. Oh my word. And what you'll be interested in is the flame graphs. So flame graphs, how many of you are aware of flame graphs? Okay, majority of the room. Oh, perfect. So I have an application that is running, and it's basically a Java application. And you can see here that what's consuming is like Spring, because yeah, why not? And then a Lambda thing. And then you can see here that the write-share controller is consuming almost 80% of my memory. The order car, and then going back to find the service vehicle, which is a method, you would assume that I've opened the code, which I assume I didn't. Project CP. Perfect. So go into my application. I said I have the order service, and then where I was. Hello. Okay. So I was in the car service, order service, find nearest vehicle. So basically, this is how it works. Check in what's running, find nearest vehicle. I just go into check drivability if it's a car, and then I'm intentionally adding here whenever it's the zone that is EU North, or the region that is EU North, and I'm calling the force mutex, and mutex basically is adding kind of a slowing down my application. I can go a little bit in details, and having picking only a car and picking another region, for example, US West, and you see that the application or the service is not suffering from the same thing. However, if I picked, hello, okay, what was the region again? EU something? North? Are you sure? Yes, you're sure. And then it's, no, that wasn't North. Okay, West? There are only 4. Okay, there's not that. Restart. Okay, tag. Hope this time it works. Yeah, EU North, yes. And then you can see, okay, it was North indeed. And then you can see that it's back again, or not. Yeah, you can see that it's back again and also only affecting EU region. So that's basically how it works. You deploy the code, you check that patterns have changed. You can add some tags basically to narrow down your possibilities, fix hotspots, which affecting which, so you know the possibilities that you have, and then go back and fix the stuff. I'm 2 minutes over time. That's basically it. Thank you for tuning up early in the morning. I hope that wasn't much.